Okay, so hello everyone. Welcome back to our Toronto AI in Robotics L seminar. Today we are glad to have Heng from MIT to give a talk on Certifiable Outlier-Robust geometric perception, robots that see through the clutter with confidence. Heng is an incoming assistant professor of electrical engineering in the School of Engineering and Applied Science at Harvard University. He is currently a final year PhD candidate in the Laboratory for Information and Decision Systems at MIT, working with Professor Luca Calone. He holds a bachelor degree from Tsinghua University and a master's degree from MIT, both in mechanical engineering. His research interests include large-scale convex optimization, semidefinite relaxation, robust estimation, and machine learning, applied to robotics and trustworthy autonomy. Heng is a recipient of the Best Paper Award in Robot Vision at the 2020 ICRA, a Best Paper Award honorable mention from the 2020 IEEE RAL, and a Best Paper Award finalist at the 2021 RSS conference. He is a class of 2021 RSS pioneer. So welcome, Heng. We are all looking forward to your talk, and please feel free to take over.
Okay, thank you for the very nice introduction. And yeah, so it's very happy to be here today, virtually to talk about my research, Certifiable Outlier-Robust geometric perception. And my goal is that hopefully by the end of today's talk, you'll be convinced that certifiable perception is promising to enable our robots to see through the clutter with confidence. So, in today, I think, in the Toronto AIR seminar, the goal is to be more interactive and, to have more discussion. So feel free to stop me if you have questions that you want me to clarify during my talk. But, eventually I also leave time in the very end for, more high level discussion. So as a robotics researcher, I'm very happy to see that robotics has been growing very fast over the last few decades. So we now have robots that can drive themselves, robots that can fly into the sky, robots that can probe into space and other planets, as well as robots that can potentially save human lives. So as we start deploying robots and autonomous systems in these safety critical and high integrity applications, one of the most important questions becomes, are robots safe? And can we trust our robots to do what they have been designed to do? So since autonomous driving is perhaps the robotic application that is most related to our daily life, I want to use self-driving now as an example to illustrate how safe our robots are at this time. So I want to broadly categorize safety into two aspects. On the left-hand side, I have hardware safety, and on the right-hand side, I have software safety. So when talking about hardware safety, a key factor is called crashworthiness, and it's defined as the ability of a structure to protect its occupants during an impact. So after many decades of research in mechanical and also materials engineering, especially these crash tests, we now have cars on the road that have very good hardware safety. Even if drivers can make mistakes and sometimes get into accidents, we know that our cars can help protect our lives. And on the other hand, when talking about software safety, a key factor is called trustworthiness. And it's defined broadly as the ability of an algorithm to be relied upon. So here, the sad news is, although we're doing pretty good in terms of the crashworthiness of our hardware, we're actually doing pretty bad in terms of the trustworthiness of our algorithms. So here I'm citing a recent article that has the title, Americans Still Don't Trust Self-Driving Cars. And this article has a few statistics to support its claim. For example, it says that nearly 3 in 4 Americans say that autonomous vehicle technology is not ready for its prime time. And about half of them say that they will never get into a taxi or ride-sharing vehicle that was self-driving. And even worse, about 20% of them just think that autonomous vehicles will never be safe. And in addition to these statistics, I believe most of us here today have seen videos like this one showing an autonomous vehicle making a mistake that a human driver will probably never make. So after seeing these statistics and also this video, I believe a question that is common now in our mind is it even possible to design safe and trustworthy robotic algorithms? So I believe the answer is yes. And in today's talk, I want to tell you my research in designing safe and trustworthy robot geometric perception algorithms. So I want to first tell you what is geometric perception. And then I want to highlight the issue of outliers and the theoretical intractability caused by outliers in geometric perception. And then to mitigate this theoretical intractability, the main contents of today will be devoted into presenting a new paradigm for designing geometric perception algorithms that are both tractable and also trustworthy, that we call the certifiable perception paradigm. And specifically, I want to present you two algorithms in this certifiable perception paradigm. The first one is an estimator, and the second one is a certifier. So let's, with this high-level overview of today's, contents, now I want to first tell you what is geometric perception. So geometric perception, loosely speaking, is just the task of estimating geometric models from visual measurements and possibly sensor priors. For example, let's take a self-driving car as an example again. It has to perform a wide range of geometric perception tasks while it's driving on the roads. For example, it has to do pose estimation, localization, mapping, 3D reconstruction, and object detection. And specifically in today's context, I want to use object detection and 3D reconstruction as two of the major running examples. And in today's context, object detection is the task of detecting and also estimating the 3D rotation and translation of a given 3D object from either 2D images like this one or 3D point clouds. And then 3D reconstruction is a task of merging a pair of LiDAR or RGBD scans taken at different space and time to reconstruct, hopefully, a partial view of our 3D environment. So now let me use this simple object detection example to illustrate what do we mean by outliers and the theoretical intractability caused by outliers in geometric perception. So in our object detection example, suppose our robot has taken an image of an incoming 3D vehicle like this one. And suppose also our robot has an exact 3D model of this vehicle in this memory. So now the task of object detection is to detect this incoming 3D vehicle in this 2D image, and then to also estimate its 3D rotation and translation with respect to the robot's own coordinate system. So in this case, a typical perception pipeline works as follows. So the robot perhaps first uses a neural network to detect 2D semantic key points in this 2D image and to establish matches or correspondences between this 2D image and the 3D CAD model. So for example, here I'm showing you detections of the wheels, the mirrors, the doors, and so on. So this step is typically called feature matching and is known as the front end of the perception pipeline. So in practice, due to various sources of uncertainties and also imperfections, the front end can typically make mistakes and generate a set of wrong matches or wrong correspondences that we call outliers. So now the goal of this robot is to estimate the 3D rotation and translation of this CAD model using this set of correspondences that are corrupted by outliers. And the robot typically performs this estimation by solving a mathematical optimization problem. And this is referred to as the model estimation backend of the perception pipeline. So now I want to tell you a key negative result in this perception pipeline, specifically about this model estimation backend. So this negative result says that outlier-robust estimation is NP-hard and inapproximable. So basically, to translate this theory, what the theorem has told us is that when there are outliers in the given set of correspondences, then it is impossible to design a single polynomial time algorithm that can guarantee to solve this model estimation problem to global optimality. So due to this theoretical intractability, much of the research efforts of our research community has been devoted into designing algorithms that run very fast, and in real time, but then compromise on the optimality guarantees. And one of the most famous examples is called RANSAC, which stands for Random Sampling Consensus. So as this name suggests, RANSAC works by randomly sampling a subset of this given set of correspondences until some satisfactory solution is found and some consensus is reached in the sampled subset. So the result of RANSAC is pretty good. In most cases, RANSAC is going to give you a correct estimation like this one. But in difficult cases, for example, when there are many outliers or wrong detections in this case, then RANSAC will fail and give you a wrong estimation, potentially looks like this one. So, in safety critical applications, which is a primary goal of my research, perhaps failing is not the worst case. So the real issue here is that RANSAC and other similar types of heuristics methods can fail without giving you any notice. So what I mean by failing without giving any notice is that these type of algorithms are not designed to be able to differentiate between a correct estimation like the one on the top and a wrong estimation like the one on the bottom. So this drawback makes these types of algorithms untrustworthy and perhaps not suitable for our safety critical applications. So hopefully now from this slide, you can see that we are in sort of a conflicting situation. Because on one hand, the theory has told us it is impossible to design a polynomial time algorithm that can guarantee to solve this problem correctly. But then on the other hand, if you want to deploy these algorithms into our safety critical applications, then we need performance guarantees on our perception algorithms. So the rest of this talk will seek to mitigate this conflict, but presenting a new way of designing this model estimation backend that is both tractable and trustworthy, that we call the certifiable perception backend. So the unique feature of this certified perception backend is that it not only produces model estimations like the one on the right-hand side, but it also produces a certificate of correctness when the estimation is indeed optimal, and a certificate of suboptimality when the estimation is not correct. So, before and this, this unique feature of certifying success and also of declaring failure makes certified perception, especially, in favor for our safety critical applications. So before I dive into the technical details about how we have designed such a certified perception backend, I want to now sort of also draw a boundary for certified perception. So what I want to say here is that certifiable perception only talks about how we can design a certifiable perception backend, which is whose focus is really in solving this mathematical optimization problem to global optimality. What we assume is that there is a front end, typically based on deep learning these days, that can give us a set of correspondences with reasonable quality. So of course, this assumption of this front end giving us a set of correspondences with reasonable quality does not always hold in practice. But in practice, how do we verify this assumption? And indeed, how do we certify the correctness of these deep neural networks is another interesting challenge, and it's a topic of its own interest, and it's beyond the scope of today's talk. Although in the final discussion phase, I do hope to talk something about how we can merge these two, the front end and back end together. But for now, it's important to notice that we are now only focusing on this model estimation backend. So with this clarification, now I want to dive a little bit deeper into how we have designed such a certifiable perception backend. And specifically, I want to present you two algorithms in this certified perception backend. And the first algorithm is an estimator that is designed to estimate geometric models from this set of corrupted correspondences. And what is worth notice is that our estimator is designed to be just like a heuristic method, just like RANSAC, which means that when the data is somehow good, our estimator can give us a reasonable, correct estimation. But when there are many outliers in the given set of correspondences, our estimator will also fail and give you a wrong estimation like this one. Although our estimator is designed to be just like a heuristic method like RANSAC, it actually offers many advantages in terms of robustness, accuracy, efficiency, and generality, which I hope to show you in the later examples. And then the second algorithm in this certified perception backend is a certifier that is designed to safeguard this estimator. So if specifically, when the estimator has succeeded in giving you a correct estimation, then the certifier will return you a check of global optimality. But then on the other hand, when the estimator has failed, then the certifier will give you a check of suboptimality and declare failure in this case. What I'll also be able to show you later is that our certifier most likely will be able to escape these suboptimal solutions and give you, better and certified optimal solutions. So in this certifiable perception paradigm, you can see that our estimator is designed to be robust and also fast. But then our certifier is the one that is giving us rigorous performance guarantees and adding a layer of trustworthiness on this certifiable perception backend. Last but definitely not the least, I want to remark that both of these algorithms are actually general purpose and it can be applied to more than a few perception applications, which I'll show you in later examples. So with this high-level overview of how we have designed such a certifiable perception backend, now I want to dive, little deeper into the technical details of both of these algorithms. But before doing these technical, details, I want to sort of, remind you that I've told you from the very beginning, the essence of this model estimation backend is solving a mathematical optimization problem. So what exactly is the mathematical optimization problem that we are trying to solve that can give us robustness against these outlier detections from the front end? So, hopefully, and luckily, the machinery of outlier robust estimation has provided us with a systematic answer. So in robust estimation, our goal is to estimate a geometric model from a set of visual measurements or data. And the goal here is really lies in this unknown model X that belongs to some manifold or some group X. And for example, in our object detection case, the measurements here are the matching 2D and 3D semantic key points. And the model to be estimated is the 3D rotation and translation of this Kkt model with respect to the robot's own coordinate system. And then there are really two key ideas in this outlier robust estimation framework. So the first key idea is to design a residual function that we denote as R here that basically quantifies how well an unknown model X can explain my visual measurements ZI. So in our object detection case, the residual function can be designed as the so-called reprojection error function, which basically measures the pixel level distance from a given 2D semantic key point to the corresponding 3D semantic key point reprojected back into the image plane, as shown by this yellow line on this image plane. So intuitively, this residual function is a scalar function that should evaluate to 0 when the model is a perfect fit. And the second idea in outlier robust estimation is to use a robust cost function that we denote as rho here to gain robustness against large residuals, which are basically outlier detections that cannot be explained very well by any geometric model. So here I want to give you sort of a pictorial overview of a family of robust cost functions in comparison to the least squares model that we are all very familiar with in engineering and science. So from this pictorial overview of this family of robust costs, you can see that a common feature of all these robust cost functions is that they are trying to flatten the curve when the residuals become too large so that the estimator can gain robustness or be less sensitive to the large residuals caused by outliers. And among this family of robust cost functions, I want to highlight the cost function that is called the truncated least squares cost function. And the reason I like this truncated least squares cost function is that it is really intuitive, and it's just based on this least squares model that we are all very familiar with. So given this least squares model that we all know, robust, the TLS or the truncated least squares cost function picks a threshold that we call C bar square to separate inliers or outliers. And then we use this threshold C bar square to truncate the least squares model. And then after this truncation, we realize that we are still penalizing our inliers or the good measurements using the least squares model, but then we are discarding the outlier measurements from our estimation by setting their objective function to be a constant. And realize that this truncation is realized by this inner minimization that is highlighted in blue in this optimization framework. So although this TLS estimation framework is known to have very good robustness against outliers, it is actually not very common in robotics and even in computer vision. And the reason is partially due to the fact that we are now dealing with an optimization problem that is not only non-convex, but also non-smooth. And therefore, it is very difficult to globally solve this problem to the desired solution. So the first algorithm in this certifiable perception backend is that we have designed an estimator that can solve this truncated least squares cost function in general robust estimation much better than existing algorithms. So in the following, I want to present this estimator for this truncated least squares cost function, but it's important to recognize that this estimator is indeed general for the other robust cost functions as well. And the unique or the crux of this estimator is that we've used an idea called graduated non-convexity. So this is a very classical idea in early computer vision, but it's somewhat forgotten in these in modern robotics. And our contribution is to show that this graduated non-convexity can reshine in the context of robust estimation. So the idea of graduated non-convexity is indeed very simple and intuitive. So the idea here is that, although we don't know how to directly optimize this truncated least squares cost function because it's non-smooth and non-convex, what we do know is how to solve, the least squares model for a majority of perception problems. So therefore, the idea of graduated non-convexity is that we can approach this truncated least squares cost function by first solving this least squares model, and then gradually change the shape of the cost function until it converges to the original truncated least squares cost function that we started with. So now the audience will ask me, how do we optimize each of these intermediate blue curves? So the idea here is that we've used another very classical but somewhat forgotten result in early computer vision that is called Black-Rangarajan duality. And then using this Black-Rangarajan duality result, we've designed an optimization strategy that is both based on ordinating minimization. In the interest of time, I will not be able to tell you the technical details of both of these results. But what I want to show you here is a simple video that illustrates how GNC works in a simple example. So in this picture, the surface plot is plotting you the landscape of the truncated least squares cost function. And as you can see, the difficulty of optimizing the TLS cost function is that there are many local minima in this surface plot, which means that if you use a naive optimization strategy, it will easily get stuck in one of these local minima and without being able to converge to the central global optimal solution that we're looking for. And the idea of graduated non-convexity is that we're not going to directly solve the original cost function, but we're going to optimize a smooth version of it, which is the least squares model. And then we are going to gradually add more and more non-convexity to this light blue curve until it converges to the original truncated least squares cost function. And then in solving this sequence of optimization problems, the trajectory of the optimal solutions will hopefully converge to the central optimal solution. So this simple idea as illustrated in this video can actually be applied to much more complicated robot perception problems. For example, here I'm showing you the running history of GNC for the post-graph optimization problem in simultaneous localization and mapping. And from this video, you can see that despite that there are many outliers or wrong measurements in the original sensor data, GNC can actually reconstruct the 3D map and also the robot trajectory with very high accuracy. So due to this, the simplicity and also the practical performance of the GNC algorithm, now it is in fact part of the official MATLAB navigation toolbox, and it's also implemented in popular SLAM packages such as GTSLAM. So GNC turns out to be, a general algorithm for many perception problems. So here I'm showing you a gallery of 5 perception problems where you can see that GNC achieves a robustness level against about 80%, 70%, or even 90% random outliers in these across these applications. So what I want to do now is to zoom in into 2 of these specific applications and to show you the practical performance of GNC compared to other algorithms. So the first application I want to showcase you is really this object pose estimation problem from point clouds. So in this application, we're given 2 point clouds. The first one is a template, and the second one is a scene that contains a partial observation of the template. For example, here to identify the 3D rotation and translation that can best align this blue bunny to this magenta scene. And in this case, a straightforward idea is to apply graduated non-convexity given this set of corrupted correspondences. But in this case, we observe that GNC is typically robust against about 80% random outliers. But then in this point cloud registration problem, it is actually very common to have an extreme number of random outliers, such as over 90% or even over 95% random outliers. So how do we boost the robustness of GNC to handle these extreme number of outliers? So me and my collaborator, Jinnan Shi, we've designed another general purpose algorithm that we call Robin that can prune or remove a majority of these wrong correspondences before running this gradual non-convexity. So in the interest of time, I will not be able to tell you the technical details about this graph theoretic outlier pruning method called Robin, but I really encourage you to read our Robin paper for more technical details. So then combining this Robin and GNC algorithm, we call our final pipeline a teaser. And here I want to showcase you the practical performance of teaser compared to other algorithms. So in this plot, you are seeing that in the x-axis, we are plotting the percentage of random outliers in the original given set of correspondences. And then on the y-axis, we are showing you the rotation estimation error in degrees with respect to the ground truth. And in this set of algorithms that we are benchmarking against, here the algorithm teaser++ is our teaser algorithm with a fast C++ version. And we're benchmarking against other state-of-the-art algorithms such as running ransack for even 1 minute, which nobody will do in practice. So and in this case, you are seeing that in this high outlier regime, teaser and teaser++ are the only two algorithms that can return accurate estimations even in the presence of 99% random outliers. And then in the right-hand side plot, I'm showing you the runtime of teaser compared to other algorithms. And you can see that in this plot, teaser++ is also the fastest algorithm, and it can typically run in milliseconds. So we also tested teaser on merging a pair of RGBD scans, which are typically more noisy than the LiDAR scans. And then in this case, we're using a deep neural network that is called 3D SmoothNet to give us putative correspondences between a pair of RGBD scans, such as the one showing on the left-hand side. And then on the right-hand side, we're showing you the scan matching result of teaser++. And you can see that teaser++ is able to merge this pair of RGB scans to very high accuracy, despite the large number of outliers in the original given set of correspondences. And then this table here showcases you the overall performance of teaser++ compared to ransack in this entire data set, which contains about 1,600 pairs of RGBD scans. And then from this table, you can see that in some of these sub data sets, teaser++ is able to improve over ransack by about 5 to 10% in terms of success rate. And to the best of my knowledge, the accuracy result or the success rate here you see by teaser++ is still the highest in today's literature. And then in the, I've told you from the very beginning that this estimator is also a general purpose algorithm. So the second application I want to showcase you is this vehicle pose and shape estimation problem from RGBD cameras. So in this application, we are seeing an RGBD image, and we only know our object is a car, but we don't know the exact 3D model of this car in the robust memory. So in this case, we assume the unknown CAD model can be parameterized by a large shape of existing car shapes, which is the so-called active shape model. And then using this active shape model, we can actually design GNC and Robin for this specific application. And on the right-hand side, I'm showing you the performance of our algorithm on the challenging Apollo-Scape self-driving data set that is collected in the urban area of China. And then from this video, you can see that our algorithm is able to reconstruct the shape and pose of a wide range of cars in the cluttered urban area of China. And then in this table here, I'm showing you the overall performance of our algorithm, which we name Pace Sharp, compared to the other state-of-the-art techniques, which are purely based on deep learning. And you can see that with this model-based approach, we can actually significantly outperform these previous state-of-the-art. So, so far I've told you the high-level intuition of our estimator, but I've told you from the very beginning that our estimator is also designed to be a heuristic method, which means that our algorithm can actually fail, and when it fails, It does not give you any notice of failure. For example, in the original Apollo-Scape dataset, you can see that our estimator often gives us correct estimations like this one, and this one. But in difficult cases, like in this case, when the target is actually very close to the robot, and actually we only have a partial view of this target, then in this case, our estimator will also fail and give you an estimation that does not make sense. So I want to motivate the second algorithm in this certifiable perception backend by proposing this question that how can a machine or an algorithm certify its own success and detect its own failure, and even to correct its own failure, like the ones on the right-hand side. So this second algorithm in this certified perception toolbox answers precisely this question. And in order for us to understand how this certifier works, please bear with me to first present you a general mathematical framework that can allow us to solve non-convex optimization problems with certified global optimality. So this slide is going to be mathematically dense, but I will try to walk you through this slide very slowly so that we can all appreciate the technical meat in this slide. And then after this slide, I will directly go to the results section so that we can wrap up my talk and give you time for the discussion. So recall that the estimator is trying to solve this truncated least squares estimation problem that is not only non-convex but also non-smooth. And then the first thing that we want to do here is to get rid of this non-smoothness of this cost function. And we do so by leveraging this identity that the minimum of two real numbers a and b can be equivalently written as the minimization over a binary variable theta that is either plus or minus 1 that selects between this number a and b. And then using this simple identity, we can rewrite the original cost function into this joint optimization over both the original geometric model x together with a set of binary variables that indicate whether or not the i's measurement is an inlier or an outlier measurement. And then for a majority of fundamental perception problems, these joint optimization now belongs to a class of continuous optimization problems known as the polynomial optimization problem. So notice that here the reformulation between from this truncated least squares estimation to this polynomial optimization can actually be generalized to other robust cost functions. So now that we've reformulated this non-smooth optimization problem into this smooth optimization problem known as POP, the difficulty still remains because this polynomial optimization is also in general a non-convex optimization problem. Therefore, it is very difficult to optimize it to global optimality. So here comes the key step in this certifiable perception paradigm, which is to relax this non-convex polynomial optimization problem into a semi-definite program, or SDP in short. And we do this relaxation using the machinery called Lassier's hierarchy of moment and sum of squares relaxations plus basis reduction. So notice that here the machinery of how we do this relaxation is actually second order for the purpose of today's talk. But really, I want you to focus on why do we want to relax this polynomial optimization problem to this semi-definite program. So the reason is actually twofold. So the first reason is that this semi-definite program now is a convex optimization problem, which means that we can solve this semi-definite program to global optimality in polynomial time. And then the second reason is that after solving this semi-definite program, we can not only get a candidate estimation to the original polynomial optimization problem, but also we can get an optimality certificate to the original problem. So let me explain you how this optimality certificate works. And it's actually very simple. So let me denote, POP star as the unknown global objective value of the original POP, which we don't know how to compute in polynomial time. And let me denote SCP star as the global optimal value of this convex SCP, which we do know how to compute in polynomial time. So because this semi-definite program is the convex relaxation of the original POP, we know that this SCP star is a lower bound for the original POP star. And now, assume we can solve this SCP in polynomial time, we can actually, using a procedure called rounding, we can get a candidate estimation to the original POP polynomial optimization problem. And let us denote or evaluate the objective value of this POP at that candidate estimation, and let's denote that value as POP hat. So because the original POP is written in minimization form, we know that any candidate estimation or any feasible solution gives us a valid upper bound for this POP star. So notice that by solving this SCP, what we effectively create is a bracket that sandwiches in between this unknown POP star that we don't know how to compute. So if indeed, we compute the relative distance between this upper bound and the lower bound, and if this metric that we call suboptimality that we compute is numerically 0, then we can certify that this POP hat or this SCP star is indeed the global optimal value that we want to compute. So in practice, we solve this semi-definite program, and we do empirically find that this relaxation is indeed tight, even in the presence of 90% random outliers. And what I mean by exact or tight is that the bracket is indeed numerically 0. So now that I've told you this powerful semi-definite relaxation framework that can certifiably solve the original non-convex problem to global optimality, does that mean that we can just directly apply this problem to any non-convex problem that we care about in robotics? So the answer is actually no, and in fact this problem is still not solved. And the caveat is that although we can form this relaxation, we can form this semi-definite program, but it turns out there are no existing convex optimization solvers that can solve these SCPs to sufficient accuracy. And there are two reasons behind this caveat. So the first reason is that these semi-definite programs, although they are convex, they actually have very high dimension compared to the original non-convex problem. And these large-scale SCPs will make generic interpolation methods run out of memory on an ordinary workstation. And then the second reason is that these large-scale SCPs are not only high-dimensional, they're also degenerate. So degeneracy here is a property that will make first-order methods converge very slowly and make the Buehler-Monteiro factorization method difficult to be applied. So now that I've told you there are no existing solvers that can solve these these large-scale SCPs to sufficient accuracy, what do we do now? So eventually, what we do is.
Ask a question? Apologies for the interruption. So I was wondering, even if you had a great SDP solver, would you expect that the suboptimality coefficient is actually 0? I mean, that would probably never happen, right?
No, it actually happens almost all the time. So
Really?
the suboptimality gap you get is actually we typically compute it, and you can look at our paper. We have a box plot of it. Usually, especially when the outlier rate is not very high, and the outliers are random. For example, below 90%, you get a suboptimality gap that is 1e minus 9, 1e minus 10, or 1e minus even 12, something like that. So it's actually numerically 0. So that's the surprising thing about these relaxation, and that's something we don't know how to explain. The theoretical study hasn't caught up yet.
Got it. Thank you.
Yeah, that's a very good point. And so I've told you that there are no existing solvers that can solve these SCPs. What we end up doing is that we've designed our own SCP solver that's called Stride that actually blends solving the POP with solving the SCP. So I'll just give you a one-slide overview of how we have designed such a solver Stride, and I'll leave the technical details, offline if you guys are interested. So given this truncated least squares estimation framework and its semi-definite programming relaxation, so what Stride does is to first use any type of local method or heuristic method, for example GNC or Randstad or even local search from a random initialization. And using these kind of local methods or heuristic methods, we can get a candidate estimation to this non-convex problem. So if the candidate estimation is indeed optimal, then Stride will kind of lift this low-dimensional solution to the high-dimensional vertex of this semi-definite programming. And then in the convex optimization problem land, then we're gonna be able to certify the optimality of this correct solution. So if indeed the optimal, if on the other hand, the heuristic method has returned us a wrong solution, then Stride will lift this low-dimensional solution again to this high-dimensional STP, and we will be able to certify or detect the failure or suboptimality of this wrong solution, and we will also be able to escape this suboptimal solution and give you better optimal solutions. This sounds too good to be true, but in the next 2 slides, I wanted to give you sort of an high-level overview of how this algorithm works. But in the interest of time, I will simply skip these 2 slides and give you, sort of the results of this certifier. The first thing I want to show you here is the kind of the scalability and accuracy of our solver compared to existing algorithms. So we benchmarked, tested our algorithm Stride compared to other solvers on this outlier-robust WABA problem. That is basically the point cloud registration problem that we've seen before without estimating the translation. So basically, given 2 sets of point clouds, we are only interested in estimating a rotation to align the 2 point clouds. So here, the table here shows you the results of our benchmark. And now let me walk you through this table, column by column. So the first column here is the dimension of these problems. So in here, the number D indicates the size of the original polynomial optimization problem. So basically, what's the dimension of the variable that we're trying to optimize? And then the number N and M here are the dimension and number of constraints of the semi-definite program. And you can see that the STP, indeed has much higher dimension than the original polynomial optimization problem. And then the metric here, which is the second column, we have a bunch of metrics to evaluate how good the solutions are. So the first 3 metrics are the Kkt residuals for the convex SCP. So for people who don't know the Kkt residuals, these are basically a set of metrics. If they are 0, then they indicate that we found the optimal solution of the convex SCP. And then the fourth metric here is the suboptimality gap, which Florian asked about this metric. So this suboptimality gap, when it's numerically 0, it indicates that we've actually found the optimal solution of the original non-convex problem. And finally, the metric here is the runtime in seconds. So let's look at the performance of different types of solvers. So the first type of solvers are the interior point methods, which I believe a lot of us here know about these solvers. So these are the go-to solvers for solving semi-definite programs. And and 2 of the most popular packages are SCPD3 and MOSAC. And for these type of solvers, you see that they can solve these low-dimensional problems or small-scale problems into very high accuracy, but then they quickly run out of memory on the ordinary workstation. And then the second types of solvers that we benchmark against are these first-order methods, which are typically based on projected gradient descent or even augmented Lagrangian. And then you see that these solvers they actually are memory efficient, and they actually do not blow up your memory. But the downside is that these algorithms, indeed, because of the degeneracy property that I've mentioned, they converge very slowly, and they cannot solve these large-scale degenerate SCPs to sufficient accuracy in a reasonable amount of time. Therefore, they cannot give us an accurate suboptimality gap of that is numerically 0. And you can see some of these numbers are, for example, 10%, 1%, which you don't know if they are indeed optimal or not optimal. And then in the last column here showcases you the performance of our solver Stride, which you see that it's not only accurate but also scalable. And in fact, it turns out to be the only solver that can solve these degenerate large-scale SCPs on this WABA problem. And you can see that it can accurately solve SCPs with 3 million of linear constraints, which is actually a performance that is it's of its own interest for the mathematical optimization community. So now that I've showed you some of these quantitative results, I want to showcase you the practical usefulness of STRIDE in our perception problems. So here, I showcase you the capability of STRIDE in certifying correctness of these accurate solutions. So you see that in the ApolloScape dataset, when our algorithm PACE gives you an accurate estimation, in terms of these very low rotation and translation estimation error, STRIDE is indeed able to give you accurate or numerically zero suboptimality gap. But if you look at the runtime, you see that our solver STRIDE is still far away from being real time. But to the best of our knowledge, this is the first time that we can certify problems of such high dimension, to this very high accuracy. And then in this second example, I'm showcasing you the another perception application that is called satellite pose estimation, which in this case we are trying to estimate the 3D rotation and translation of this satellite given a set of detections that are corrupted by random outliers. And from this slide, you can also see that when the estimator, which is in this case is actually a RANSAC that we started with, when RANSAC succeeds in estimating these these correct solutions, our solver STRIDE can give you accurate numerical suboptimality gap that is numerically zero. And because these problems are relatively low dimensional, you can see that the runtime here is a little bit friendly. They are sometimes half a minute or even 1 minute or 2 minutes. So with suitable hardware speedup or algorithmic speedup, we do hope that these algorithms can potentially run in our robotic hardware in real time. So in the last slide, I want to showcase you the capability of STRIDE in escaping some of these suboptimal solutions, which is a fascinating feature for this solver. So in the first row here, you see that our estimator GNC has failed in these three examples. In these three examples, you see that the object is either too far away or too close by, and therefore the front end gives us too many wrong detections. And then in the second row, you see that our algorithm STRIDE is able to detect the suboptimality of these failed solutions. And then, more surprisingly, is able to escape these suboptimal solutions and give you better certified optimal solutions. That sort of concludes the today's talk, where I want to now give you a sort of a short summary of what I presented. So I started by telling you that, outlier robust perception, especially the backend, is theoretically intractable. And then to mitigate this theoretical intractability, the main contents of today has been the certified perception backend, where the algorithm itself is both tractable and also trustworthy. And specifically, the way that we realize this certified perception backend is by designing two algorithms, where the first algorithm is an estimator that is fast and robust by the heuristic method. And then the second algorithm, which is the certifier, which is based on this semidefinite relaxation machinery and a new STP solver that enables this large-scale SDP solutions. So most of the algorithms today I presented are already on GitHub, so feel free to try them for your own problems. And in the end, I want to sort of thank all my amazing collaborators, especially to these two mathematicians in the National University of Singapore, which actually they are the one of the main push forces behind the new STP solver called STRIDE, and all the funding agencies behind these projects. And with that, I want to thank the organizers again for inviting me for a talk, and I'm open to any questions and discussion from the audience. And I'm sorry if I've taken too much time.
It's awesome. Thank you for the great talk. And yeah, I think this now is the QA time. And any questions from the audience, please just unmute yourself and ask. Yeah. Oh, Hank, there's actually a very long question in the chat. Would you mind? Yeah, in the chat. Would you mind just, or maybe I can read them out. Yeah. So this is a question from Abhishek. So he has 4 questions. The first one is that for teaser with 99% outliers, are the outliers all random as in Gaussian distributed, or is a fraction of 99%, are they like adversarial noise? And have you tested your algorithm with adversarial outliers, or if they are just Gaussian? Yeah.
Yeah, I think this is a great question. So in the teaser plot that I've shown before, all the 99% outliers, they are random. So basically, what we do there is that we, for example, let me go back to the slide. We kind of simulate. We have the blue bunny model, which is available from the Stanford LiDAR scan repo, and then we simulate this magenta scene by randomly rotate a partial view of this blue bunny. And then the way we generate outliers is to randomly sample 3D points in the 3D space, in sort of a unit sphere or some sphere with fixed size. And then, so all these 99% outliers are random and they're not adversarial, but we have tested, this algorithm, especially our certifier with adversarial outliers, and it is in the supplementary material of the Neuros paper that we published in 2020. Of course, because the reviewers was also curious about that. So we found that when the outliers are adversarial, so of course there are many ways the outliers can be adversarial, and the specific type of adversarial outliers that we cared about was the what if the adversarial outliers themselves can form a hypothesis that achieves a lower cost than the inliers that we generated, right? So in those cases, we do found that so in that case, if the number of adversarial outliers are below 50%, then the original inliers still win. But then when the adversarial outliers and the inliers themselves are 50%, then it becomes the ambiguous case where you don't know which hypothesis is indeed the optimal solution. So for example, in the original bunny case, if you have two bunnies in the magenta scene, then you don't even know which bunny you're looking at, right? So in those cases, it becomes sort of a less well-posed problem. But then when the adversarial outliers themselves are over 50%, for example, when the adversarial outliers have 70% vote in the original correspondences, then the adversarial outliers will dominate the original inliers, and then the inliers themselves become outliers. So the outliers or inliers concept in here is per the definition of the mathematical optimization problem. So that is again, I think a nice way of how we should connect this back to this front end, right? Because it's really the front end is task relevant. So if the front end should be able to give us a set of correspondences that is targeted at finding or detecting key points that are relevant for this specific task. If I'm trying to, if I have two doors, right, then the front end should give me detections of the left door rather than the right door if I'm trying to open the left door. So that becomes as far as I think that should be the task of the front end. Of course, the back end can do something magical, which we haven't published, is when the adversarial outliers and the inliers themselves are 50%, the SDP relaxation can give you both solutions, to be honest, because it gives you a rank 2 solution and you can sort of get both solutions out of the SDP solution. But that's something that we think is less important than for the focus of today. Does that answer your question? I think let me read the second question. So second question says that does teaser and GNC rely on the outliers being symmetric? Since the cost function is symmetric, do bias outliers residuals only on the left or on the right side of the curve have any impact on the accuracy of the approach? That's a very interesting problem. As far as I know, I don't think it will do anything to the cost function because as you said, because eventually any error is going to be squared, right? So the plus and minus sign shouldn't matter in the cost function. The third question is, what's your opinion on deep learning methods for object pose estimation, since they are the preferred methods in the self-driving community? Do they implicitly handle outliers since most bounding boxes are generally stable? Yeah, I think that's a good point. I think I think, in the perception pipeline that I started with, I do think that, the deep learning front end plays a major role in giving us, or in sorting out the semantic information, right? So how do we recognize the wheels? How do we recognize the doors? Detect these, finding these reliable detections, I think is very important for the backend. But I also do think that the backend has its own advantage in giving you provable guarantees, because many of these methods, or the methods I presented today, they are certifiable, right? So they are certifiable in terms of global optimality. Of course, they are not yet certifiable in terms of the desires of the solution. So for example, an interesting question is the optimal solution always the safe solution? That's actually not always the case. And we are actually trying to find conditions under which we can guarantee the optimal solution is also the desired solution. I think really the hope or the promise lies in the intersection of both deep learning methods and these model-based methods, where I hope to combine them in a way that we can combine the expressiveness and the power of deep learning in explaining data and learning from data with the sort of the guarantees that are offered by these model-based methods. I think the last question is out of curiosity. In your introduction, you talked about using neural nets. Are you looking at certifying the front end somehow? Yeah, I think that's also a very good point. I think it's also something that I'm looking at these days. I think in the literature there are a lot of works in certifying the robustness of neural nets, and as far as I know, they typically work well in these dense layers, multi-layer perceptrons. But then I think a common feedback from people I know that who work on these neural nets is that they don't scale to these deep convolutional neural nets that are used in learning, in computer vision, for example. I think either these convolutional neural nets are too deep or they are too wide, and basically, and one thing that's interesting is that I think kind of a very a major kind of machinery for certifying neural nets is actually using semidefinite relaxations. And as I've alluded to in this talk, the kind of a bottleneck of semidefinite relaxation is that they are not that scalable. These are convex optimization problems, but they are not very friendly, to solvers. So I think there is an opportunity there is how we can, apply these neural network certification methods to convolutional neural nets that are used in these, for example, in these semantic key points detection methods. And how do they scale to the size of the neural nets used in vision? I think that's a challenge now. Of course, there may be other methods that we can leverage to certify the front end, but I think it's an open problem as of now.
Yeah, thanks for the answer. Yeah.
I think
so
there's another.
Yeah, yes.
There's another question: is any thoughts on including color and texture as part of the residual as well? Yeah, I think it could be an interesting problem to consider. I haven't tried any of that in my work, to be honest, and but I do know there are some works considering these colors or textures as part of the residual. I think the interesting question to ask is, how do you kind of transform the color, right? So because for the 3D coordinates, if we apply rotation and translation to the point, it's going to transform to another coordinate frame. But what about the texture? Right? If you have color and texture, what's the map that can map the color and texture to the other frame? And are they, sort of equivariant to this rigid transformation, right? Because under different lighting conditions, the color or the texture may change in two different views. And how does that contribute to your residual? And the other interesting problem is, will the problems still scale to the extent that the current solvers allow? Typically, I think there's a, in using mathematical operation for these decision-making or estimation problems in robotics, I think a common trade-off is sort of the fidelity of the model and also the tractability of the model. So if you're trying to model many things, then of course you are having a very good model, but then how can you solve this optimization problem, right? Because this problem becomes too large that the only hope is to use gradient descent or even zero order methods, which do not typically give you any guarantees. So the best hope there is to converge to a local minima. But on the other hand, if you arrive at a model that is reasonably small, then you can use these convex relaxations to relax them into convex problems, which can give you optimality guarantees when you solve these problems. So I think the best place is, can you derive mathematical optimization framework that is reasonable, high fidelity, but also tractable to the extent that is allowed in current solvers and mathematical machinery. I'm happy, if you have any ideas about how you can include color or texture in these residuals. Are there any other questions?
Any other questions?
Couple.
Yeah, please go ahead.
So I'm wondering if you try to use expectation maximization as sort of a baseline in some of these methods. So one of the steps would be to try to guess the right data association, and the other one would be to minimize the loss based on that data association.
It's actually very interesting, and we actually have tried that in a paper that we published last year in CVPR. It was, I think, one of the interesting thing. So basically, give a few, step back a little bit. So if you look at this perception pipeline, it has this front end that is giving us data association, and then there's this back end that is giving us models based on these data association. But this is a chicken and egg problem, right? People who work on data association, they typically do not care about the back end. And for people like me who work on the back end, we assume there's someone who give us the front end. But which one should come first, right? Because when people train the front end, they need these geometric models to do kind of correspondence mining in the metric learning space. So in the paper that we published last year in CVPR, what we were advocating is this self-supervised geometric perception idea, which is, we start with some, with a kind of handcrafted feature like, FBFH in 3D point clouds or SIFT in 2D images. And then we use ransack to give us, these pseudo labels. So these labels are, rigid transformations that are not necessarily correct, but they are, we hope they are, maybe 80% or 50% or 60% correct. And then we use these pseudo labels. We just directly, feed these pseudo labels into the front end feature learning, and then we hope that the front end can still learn some reasonable, data association from this noisy supervision. And then after the front end has been trained, we're going to use the learned features to generate new data association that we feed again to ransack. So this becomes a positive loop. That we call self-supervision, but to tackle the chicken and egg problem, we use kind of a handcrafted feature to bootstrap this process. And then what we found out is that this self-supervised idea, in which case you can get rid of these ground truth labels, which typically come from structure from motion or SLAM, that can typically be very expensive or need a lot of human supervision. This self-supervised framework can actually do almost as well as these supervised oracles, and sometimes they even give you a little bit higher accuracy in terms of final test accuracy, which we suspect is because of probably training noise or other types of hyperparameters training, hyperparameters tuning. But I think the idea there is that even under this noisy supervision and noisy training, we call this noisy teacher-student loop. Even under this noisy teacher-student loop, you can still get some reasonable both data association and backend from this noisy training process. And I think some people actually kind of took this idea further, and I think some people were applying it to SLAM as well. You can, in the SLAM case, you also have a front end and a back end. But you can actually get rid of this entire supervised training by using the self-supervised way, by using handcraft features to bootstrap the SLAM process, and then you get noisy loop closures or noisy post graphs that are not necessarily 100% correct, but you still train it using these noisy labels. You can still get some good data association out of it, and then you kind of refine this process, and you hope that your teacher and students both improve with this noisy student training idea.
Gotcha.
And
Thank you.
That's actually an expectation maximization algorithm under the hood.
Yeah, it sounds promising. So the other question that I had was, you mentioned, and one of the previous questions, mentioned the front end. So I guess what type of properties would you value in a front end in order to make the solution of your SDP a bit easier? In the sense that, would you want the front end to have low Lipschitz constant, or what type of mathematical properties would you want the front end to have?
Yeah, that's a very, very good question. So I think in this slide I'm showing this this estimation contract, which is a contract which combines together with optimality can give you the safety or designers of the solution. So basically, you have some ground truth model that you are trying to recover, right? And then you are solving this mathematical optimization problem. So if the front end can give me measurements that are somehow related to this ground truth, right, in some way. So for example, if the front end can ensure me that for example, the wheel detection is at the most 2 centimeters away from the ground truth wheel solution, from the ground truth wheel position, and the door location is at most 3 centimeters away from the real door location. Basically, I'm saying that you have bounded noise on the front end detection. Then it actually makes sense for me to solve this mathematical optimization problem, right? So we can sort of derive a theorem or some results saying that if the measurements satisfy these conditions, for example, less than 20% outliers, and all the inliers have these bounded noise, then we can assure that the solution or the optimal solution of the backend is not too far away from the ground truth, right? That's something that you want to have, for example, for designing your controller, right? So in these perception-based control research, typically control engineers, they need some bounded error in these state estimation, right? So how do we get this bounded error from these state estimation, in particular from geometric perception? So that's the requirements I want for my perception front end. But the question is, how can the front end give me these guarantees, right? How can the front end, I've trained the front end that perhaps works on all the training data set, but now I give you a new image, that the front end has never seen in the training data set. Yeah. How do I know that the front end is going to be able to detect the location of the wheel with at most 2 centimeter estimation error? So how can you give me such a bound on the detection error? And one way that you suggested is to use the Lipschitz constant, which I think is promising, because if you can somehow bound the distance from the new image to some image in the existing training data set, and if the distance in some way or even in some latent space is not too far, then if the Lipschitz constant of the network is not too large, then you can guarantee that the output of the front end is also not going to be too crazy, right? So that's one way of giving you such approvably correct estimation contract. But here, I think there are two challenges, which is the first challenge is how can you reasonably bound the distance in the input, right? Because all the natural images, they look too different. Due to different kind of lighting conditions, I'm looking at the same car, but in different perspectives, they may look drastically different if you look at the raw pixels. So how do you compute a distance that clusters, similar images together and, makes, dissimilar images far away in the feature space. And the second challenge is how can you compute a tight Lipschitz constant in these neural networks? There are tractable ways of computing the neural network Lipschitz constants, for example, based on linear programming. But usually these linear programming, relaxations, they are typically very loose, and they give you Lipschitz constants that are very loose, which can be very large, so that you don't get any reasonable bound on the output. Or you have more powerful relaxations such as semidefinite relaxations or Lasser's hierarchy. But then these relaxations, they can give you tighter bounds, but they're much less tractable. You can't even solve these semidefinite programming problems. So there's this natural trade-off again in how do you get the tight you get a reasonably tight Lipschitz constant bound, but then you also solve this problem to the extent that's allowed by existing solvers. I think that's another challenge there. I think if we can tackle these two challenges, we are kind of close to answering this question.
Got it. But I think there are papers that sort of say that architecturally design the network in a way that you can guarantee what the Lipschitz constant is going to be.
Oh yeah, I think so. I think usually I haven't looked very closely into those line of research, but I think that some people have sort of regularization in the loss function, so that the network tends to have a smaller Lipschitz constant. But I think, as far as I know, they're not guaranteed, right? So usually it's like you train the network with this loss function that regulates the Lipschitz constant, but still you have to eventually certify if the trained network indeed has the desired bound on the Lipschitz constant. Right? I think it will be much nicer if you can design a network in this way, and then you guarantee it's never gonna the Lipschitz constant is never gonna blow up. I think that will be interesting too.
Maybe we can talk offline, because I have a paper in mind that guarantees it architecturally.
Sure. Wow, that'd be nice. I can email you later.
Yeah, that'd be great.
Okay. Thank you.
Yeah, thank you.
Other questions? Well, these are great questions. Thank you very much.
Yeah, thanks for the talk. It's really good. I wish we had a bit more time to go through Stride. But I had a question more about, so in your teaser paper, you were able to solve the registration problem with a truncated least squares cost, and you didn't have to resort to using Lasser's hierarchy or something similar to that, where you're drastically increasing the dimension of the SDP. So I was just wondering if, also you were able to do that by just kind of adding, I think, a few constraints, redundant constraints to the SDP in order to tighten it.
Okay.
So I'm just wondering, like what types of problems are amenable to that sort of approach, and what types of problems require you to go to that very high dimensional SDP? Or if there's a way of characterizing that.
Yeah, that's a good point. I think in the teaser paper, so the story is that we started this line of research without being aware of this Lasser's hierarchy, or Lasser's hierarchy of moment or sum of squares relaxations. And then we, in 2019, the ICCV paper that we published, we were, kind of designing the relaxation based on Shor's relaxation. Shor's relaxation is a relaxation for QCQPs, basically for quadratically constrained quadratic programming problems. So if given a QCQP, Shor's relaxation is actually very simple, and it's not very subject to the scalability issue. But then we found that if we apply Shor's relaxation, we actually do not get a tight relaxation. So then the idea is that, can we add redundant constraints to make the relaxation tight?
Right.
And then, we wrote the paper without being aware of this, Lasser's hierarchy. But eventually, in retrospect, we finished that ICCV paper, and then we got, aware of this Lasser's hierarchy, and then we realized that it's actually equivalent to Lasser's hierarchy. So basically, what happened is that the redundant constraints we added was sort of an art, right? So people ask, what kind of redundant constraint can you add? Can you add them in a systematic way that users do not need to tune it? And then later we found that these redundant constraints are not actually redundant. They are basically second order Lasser's hierarchy or second order sum of squares relaxation. So basically, to answer your question, in the teaser's paper, we were actually indeed solving this outlier-robust WABA problem. So in teaser, we were solving the scale and then rotation and then translation. So the rotation subproblem is indeed this WABA problem in truncated least squares cost function. And as you see here, the dimension also goes very high in the end, but it goes, the dimension increases less quickly than if you apply Lasserre's hierarchy naively. And the idea here is really to use this technique called basis reduction. So basis reduction here is a technique that's a little bit of an art. So basically, this is saying that so Lasserre hierarchy has two versions. One is a dense version. One is a sparse version. So so the dense polynomial optimization basically means that if you have a polynomial optimization problem where the monomials appear very densely, then you have to apply this dense hierarchy where the dimension of the STP grows very fast with the dimension of the original problem. But then if the original POP is actually sparse, which means that some monomials actually do not appear in these optimization problems. So for example, if you are optimizing you are solving a problem with two variables, x and y, if your cost function is x squared plus y squared, then it is actually sparse because it doesn't have monomials such as x, y, and x times y, right? Because it only has x squared and y squared. So this is kind of the sparsity feature of this polynomial optimization. And then once you have these sparsity feature in the polynomial optimization problem, then you can kind of explore a wide spectrum of techniques called basis reduction, which is you can actually reduce the dimension of the STP by actually dropping some monomials in the relaxation from the Lasserre hierarchy. But then this becomes sort of an art because then the problem is which monomials should you drop, right? So will dropping the monomials affect the tightness of relaxation? Then it becomes sort of a try and error. You have to drop some monomials and see if the tightness remains, and then you have to incorporate back if the relaxation is not tight anymore. So you have to do sort of these testing, but it's not very difficult from my experience. Is because especially when you deal with this truncated least squares, so the kind of the sparsity just appears very naturally, and you will have a rough idea about what type of monomials you want to keep and what type of monomials you want to drop. And if you look at our PAMI paper, that is conditionally accepted, we have a remark there about how I think it's remark 8 or something that tells you how you can test from our experience how you should try and narrow these different monomials. And there are also software packages that helps you do this. So I think in the computer vision community, people were not so much aware of this Lasserre's hierarchy, but I think now with this Lasserre's hierarchy, Shor's relaxation is actually just a special instance of this hierarchy, and you can design much more sophisticated hierarchies that can give you tighter relaxations.
Okay, great, thanks.
Yeah, hi Hank. I have a question. So thanks for the great talk. Yeah, I'm wondering, have you heard about a paper called Superglue? Yeah, I'm just wondering. So Superglue is posed itself as the middle end between front end and the back end. Is doing a structured learning on two groups of features and establishing better correspondence. I'm just wondering, what's your view on this on Superglue? Like, do you think, like, what in your mind is the pros and cons, and does this Superglue also fit in your certifiable framework? And with such deep learned middle end, it is still certifiable?
Yeah, I think it will be. So Superglue is sort of the, like you said, it's a middle end, right? So I think Superglue is a little, so it's probably not this front end. It may be the point cloud registration. It's like you are given key points in one point cloud, and you're given key points in the other point cloud, and then with their own features. And superglue sort of give you matches, right? So you're given a set of points and the other set of points, and superglue helps you draw matches between these two things to give you correspondences that you can optimize. For example, using Randstad. I think of it as another part of the front end, or if you want to give a different name, you can call it middle end. I think front end, what we see as front end is basically everything apart from the back end, right? So everything that gives me prior data, gives me prior correspondences. We think of them as correspondences. And I think superglue, if you look, there is a classical counterpart to it, which is called graph matching. So graph matching is the idea, you have two graphs where each graph has n nodes, where each node has an associated feature vector. And your goal is to align or to find a permutation matrix or partial permutation matrix that can match these two graphs, right? So I think superglue is sort of doing this part. And to that end, I think you can sort of make it certifiable by also certifying the neural network that is designed for the superglue architecture, or you can sort of do a self-supervised way of doing this graph matching thing together with the middle end. I think that's also possible. But to be honest, I never used the superglue in my research because I think it was not intended for the problems that I was interested in. But I was kind of aware of that superglue. And so there's another thing called superpoint, right? So superpoint and superglue. So superpoint is for generating these salient points, and then superglue is for drawing matches from these salient points.
Yes, I see. Yes, thank you very much.
Yeah, but I don't think I've answered your question, but I think that's sort of my the thoughts that come off my mind when I think about these things.
Yeah, I agree. Like it's more a part of front end, and yes, yeah, thank you.
Yeah, what's your view? What do you think it's beneficial to separate this what people do these days? For example, for point cloud registration, is they do these you have 2 point clouds, then they generate one feature for 1 point, right, per point in the point cloud, and then they just do nearest neighbor search to generate correspondences. I think superglue is probably doing something fancier than nearest neighbor search that is also differentiable so that you can train it. Do you think it's beneficial to separate these two parts, or to replace the nearest neighbor search, or there's even soft nearest neighbor search with the superglue?
Yeah, according to my experience, I did have similar work. I did try their network and have implemented similar stuff. According to my experience, like neural network does have the ability to give a better correspondence based on the feature you learned. So the output
search.
Sorry?
Wait, is it better than nearest neighbor search?
Yes, it's better than just the like pairwise. It's better than considering each correspondence independently.
Okay.
And if you train the network in a whole, it will learn the structure in the neural net and can get a better correspondence out of it.
I see.
And a better thing may be like superpoint plus superglue. The whole thing is end-to-end differentiable, and you can train it like from features all the way up to the final matchings. So that could be also a very good point here. Yeah.
Okay. Yeah, makes sense.
Sorry, can you train, Chao? Can we train like superglue plus superpoint on those large scale scan data set, because there are like millions of points there, right? Or maybe like hundreds of thousands. So I guess, is it possible to train the whole model end to end in that case?
Usually you downsample first, right? Do people typically downsample first? I think they do like sort of bulk style downsampling or other types of downsampling first.
Right.
Yes.
Okay. Yeah, that makes sense. Yes. Okay. So yeah, thank you for the awesome talk and the Q&A sessions. And I wonder if there are any questions from the audience. Not. think it's already 12, and maybe we can just end here.
Yeah.
Let me stop recording.